let's take a look at what we mean by the word concavity. So let's let f be a function that is differentiable over an open interval I. So we have a nice function that's differentiable over an open interval I. If f prime is increasing, it is concave up. If it's decreasing, cannot write today. If it's decreasing, it is, we usually say concave is CC down. Now let's see what we mean by that. Let's take some functions and let's look at whether they're concave up or concave down. So here we have an increasing function, right? We have f is increasing. And then I'm going to draw another function next to it where f is also increasing. The function itself is growing as time goes on. If we have on the x-axis, if we have time, as we go further along the x-axis, we see that we're going up in the y-axis. In both cases, we're going up in the y-axis. But hopefully everybody can see that there's a clear difference between these two graphs. There's a clear structural difference. The one on the left is going to be concave up, and the one on the left is going to be concave down. And the derivative can tell us why that's happening. We have f prime in the left case is increasing. And what do we mean when we say f prime is increasing? F prime is the slope of the function. The derivative is the slope of the original function, and the slope itself is increasing. We're not talking about positive or negative slope anymore. We're talking about increasing slope. And we can see that this is getting steeper. Increasing slope means we're getting steeper over time. And on the right, we have a function that's increasing, but f prime is decreasing. Or we see that we're starting off steep and we're getting flatter over time, which means it would be easier to walk on this further to the right. You would rather be over here, whereas on the left side, you might rather be over here, because we have a function that's increasing, whose derivative is increasing on the left and its derivative is decreasing on the right. Similarly, if we're looking at decreasing functions, we might have something like this, where f is decreasing, and something like this, where f is also decreasing. But on the left, we have a function that is going from a very steeply negative slope up towards a slope of 0. And so f prime, the derivative, is actually increasing. And so we're once again CC up. We're concave up. And on the right, we have a function whose derivative, f prime, is decreasing. We're going more negative. And we again see that we're CC down on the right. And what does it mean to have a derivative that's increasing or decreasing? Well, the derivative tells us that the function itself is increasing or decreasing, right? A positive derivative means the function's increasing. A negative derivative means the function's decreasing. So let's let f be a function that is twice differentiable. Let f be a function that is twice differentiable over an interval I. Then, if the second derivative, if f double prime of x, or the derivative of the derivative is greater than 0, then what does that mean about the derivative? If the second derivative is greater than 0, that means our derivative itself is increasing. And we said if f prime is increasing, we're going to be concave up. If the second derivative is greater than 0, then f is concave up over I. And then number 2, if the second derivative of x is less than 0, f is going to be, well, that's the second derivative tells us about the behavior of the first derivative. If the second derivative is less than 0, then the first derivative is decreasing. And when the first derivative is decreasing, we are concave down. So f is concave down over I. Now this second derivative can give us some more important points on our graph. If f is continuous at a point A, and f changes concavity, or the second derivative changes from negative to positive or positive to negative at A, then A is called an inflection point. Inflection point of f. And let's see what we mean by that. So we have a graph here, and we're going to change concavity. We're going to go from CC up to CC down. Well, if we're changing from CC up to CC down, here I have some point where to the left of that point, f prime is less than 0. To the right of that point, f prime is greater than 0. So our function goes from decreasing to increasing. But over that point, f double prime is greater than 0. The second derivative is greater than 0. And what do we mean by that? Well, that means that the slope is increasing. We're going from a very negative slope up to a more positive slope. But at some point, because we're switching to concave down, so this is getting steeper in the positive direction, positive, 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 at some point, some critical point here, some inflection point, some point A, we're switching to a function whose second derivative is less than 0. We're switching to going from a positive slope to going towards 0, towards 0, towards 0, then negative. And so here we have another critical point, and to the left of that point, the first derivative is greater than 0. The first derivative is less than 0 to the right of it, because our function goes from increasing to decreasing. But we have this new point, this new value that helps us understand graphs, which we call an inflection point, which tells us when the slope itself goes from increasing to decreasing. It gives us an idea of where the function is on its way. Okay, let's do an example. Let's say for f of x is equal to x cubed minus 6x squared plus 9x plus 30. We want to determine the intervals of concavity, inflection points, critical points. Let's determine all three of these. Let's find the critical points, the concavity, and the inflection points. So f prime of x is equal to 3x squared minus 12x plus 9. And this, setting this to equal to 0, will give us the critical points. So I set that equal to 0. I see that everything's divisible by 3. I get x squared. I'll divide by 3 and get x squared minus 4x plus 3 equals to 0. So our two critical points are going to be x minus 3, x minus 1. They multiply together to equal 3 and add up to equal negative 4. So our critical points are x equals 3 and x equals 1. And then we can also find the second derivative of this function, which is 6x minus 12. and set that equal to 0, and that'll give me my inflection point. So we have our critical points. Now let's find our inflection point, which is add 12 to the other side. We get 6x equals 12, divide by 6, x equals 2. Which means we can draw another one of these graphs. We go from negative infinity to the point 2 all the way up to positive infinity. That means that we have an inflection point at 2. We're either concave up or concave down to the left and to the right of this. And now we can see where we are concave up or concave down with test points, just like we did for the first derivative. For example, I can check the point 0, and I can check the point, say, 100. Let's plug in 0 to the second derivative. Well, when I plug in 0 here, I just get negative 12. So we have a negative value, which means we are going to be concave down. And then from 2 to infinity, I can plug in 100, and when I have a really big number here, a really big number minus 12 is going to be positive. So we're going to be CC up. So here we're CC down, here we're CC up. And if we're concave down to the left of 2, that tells us something about our critical points as well. So if I want to graph this, I have the point negative, or I have the point 3, I have the point 1, and look, to the left of 2, we are concave down, which means we have to be going from negative to positive and be concave down. And then when we get to 3, we have to be concave up. And 2 is our critical point, is our inflection point. And so we can get a really good idea of the graph of this function. And all of this is to say this gives us a second derivative test. And the second derivative test tells us, let's suppose f prime of c is equal to 0, f double prime is continuous over an interval containing c. Then if f double prime of c is greater than 0, f has a local minimum at c. If f double prime of c is less than 0, f has a local max at c. And then we also have some cases, we have to write down the third case, where if f double prime of c is equal to 0, if the second derivative is equal to 0, the test is inconclusive. There are some cases where we can't use the second derivative test, and we'll talk about them in the future. But for the most part, here we have the second derivative test. And so let's do one more example. Let's find all the local extrema of x to the 5th minus 5x to the 3rd. Let's say this is f of x. And let's find the extrema of this. So first, let's find the first derivative. This is f prime of x is equal to 5x to the 4th minus 15x squared. And the second derivative, f double prime of x, is going to be equal to 20x to the 3rd minus 30x. Okay, so let's find where the first derivative is equal to 0. Well, we can pull out two x's, so we can and a 5, so we can say this is equal to 5x squared times x squared minus 3 is equal to 0. Well, this is equal to 0 when x is equal to plus or minus the square root of 3, or when x is equal to 0. And then from here, we can just look at our f double prime of x function and see what values we get. So we're going to check our three values. First, we say x is equal to 0. So f double prime of 0 is equal to 20 times 0 minus 30 times 0, which gives me 0, which means at 0 we're inconclusive. We don't know. That's that third case. F double prime at positive the square root of 3 is going to be 20 times root 3 to the third power minus 30 times root 3. And let's try to understand this. Let's try to understand this by changing f of x. Let's say f double prime of x is equal to, well, we can factor it. We can get 10x times 2x squared minus 3. And that's going to be a little easier to look at. So let's try this again. Let's say f double prime of root x is equal to 10 times root 3 multiplied by 2 root 3 squared. Hopefully we all know that's just 3 minus 3. And now we can really see that this is a positive value. We can really see that that's a positive value that came out of that. And then f double prime of negative root 3 is going to be 10 times negative root 3, so some negative number multiplied by 2 times negative root 3 squared minus 3, which is going to be a positive number. A negative times a positive, that's going to be a negative value. And so here we have when x, let's make a little table, when x is negative root 3, f double prime of x is going to be negative, which means our conclusion is going to be negative root 3. We have negative, which means we're concave down, which means we have a local maximum. This is concave down, which means our value is going to be a maximum. When we plug in 0, f double prime is 0, and so we have inconclusive. And lastly, when we plug in the square root of 3, we saw that we got a positive value for our f double prime of x, which means we have something that's concave up, which means we have a local minimum. And that is our concavity given to us by the second derivative.